Good morning, everybody. Today we're going to do these electrical schematics of both the Venus and a ZERES. We'll go through the Venus first, then we'll go through the differences between the ZERES and the Venus machines. For those of you that weren't here last week, again, how we read these blueprints, you have the page number at the bottom. And it's a grid type blueprint. So for example, B2 would contain X information. All right. These are the symbols for the electrical. You have a junction of conductors, a terminal strip, conductor, frame for a device, your grounding symbol, your protective ground, transformers, connector with plugs, limit switch, that's a normally open, limit switch, that's a normally closed, E-stop, another E-stop, proximity switch, another proximity switch, pressure switch, relay contactor, three-phase motor, fan motor, heater, lamp, contactor, three-phase motor, fuse switched, solid state relay, thermocouple, solenoid, three-phase current breaker, a push button, make contact, and a break contact. A couple of bits of information that people should be aware of. The proximity switches on these machines are PNP. We sell robots. The robots that we sell, the Wavy robots, are NPN. And but you have to keep in mind that the proximity switches on these machines are PNP. What that means is coming off of the controller for the output, you're going to have a 24-volt signal for a PNP. For NPN, coming off of the controller, you're going to have a 0 volts. And that goes to a positive 24 volts. This goes to a ground, negative 0. That's the difference between a PNP and an NPN proximity switch. The other thing that you have to remember that a lot of people don't really keep in mind when they're reading blueprints is the limit switches. So a normally open or a normally closed limit switch is the status of the limit switch when it's not being activated. For example, if you close a door and the limit switches are activated, then the conditions change. They'll go from an open to a closed position or a closed to an open position. So when you're reading the blueprints and you're looking at a contact that says, oh, this is a normally open switch, but I'm getting a reading, that's because the contact is in an energized position. And so therefore it does the opposite of what it's supposed to do. Again, I told you yesterday that it has a diagram of the location of all the switches. This is page 2 of the electrical drawings usually. And it shows you the back location of all the switches. So if you're looking at a blueprint, you don't know exactly where a switch is. You can always look at the diagram. It'll show you where it's located. For example, X1, 4, 5, 6, 7, and 8 are located inside this panel. And they give you an element layout. The element layout is this is the low voltage cabinet. It's just a layout of what the cabinet should look like. So up here you have your PLC, KE1, that's your safety relay, KE2 and 3, and a bunch of little contacts. Your 2 power supplies, a battery, a terminal strip, and a couple relays down here. The FL1, sorry, that's the that's a timer. On this page, it shows you the heater band circuit layout. So you have all your SSRs down here. The SSRs are fan cooled. So there's a little fan that keeps the heat of the temperature of the SSRs down because they do get hot. If you do run these without the fan, then they will burn up a lot easier. And usually when the SSRs burn out, they burn out in a normally closed condition, which means that you'll always have power going to your heater bands, and your heater band will override and therefore cause overheat and burning of your material. Up here you have all your fuses for your different controls, etc. And then you have your transformer for your front zone temperatures. Again, you have motor starters, more fuses over here. You have two motor starters, one for your reverse and one for your forward. You have your Q1 breaker, QM1 motor starter, and you have a couple motor starters over here. All right, so we'll start at the beginning here. Here's the diagram of all your interlocks for your safety doors. As you notice, it's running off of K18. If K18, if you open one of the doors, what it does is K18 is right here for this little limit switches on your shunt breaker. So if you open a door, the solenoid kicks out, K18 will then go from normally closed to a normally open. When it opens up, it breaks the signal going into the disconnect. Therefore, it'll de-energize the disconnect and it'll kick out the breaker. So any of these switches which are on your doors are opened, it'll kick out again K18, which is a relay, which is controlled with this contact right here. So if that loses power, then everything will die. The shunt breaker will trip the breaker itself, and the power will be lost on the machine. So again, you have a shunt breaker. If you notice, shunt breaker is on the live end of the power. It is always live. So inside the cabinet, there is a terminal switch with a terminal plate that has these connectors. And you have to make sure that you know that when you open the cabinet, even if you shut the power off on the machine, that these two lines are going to be live all the time. Unless you disconnect the power at the source, those will always be live. So when working on the electrical end of this machine, you have to be extremely cautious about these two wires, because it is 480 volts and you will feel it. And you just have to make sure that you don't touch those wires without the power being cut off at the source. This disconnect is a 250 amp disconnect. And again, I got to show you this because it's a relay, A1, A2, and it's controlling K18. Down here, it shows you the contact for that relay. So it's using pins 12 and 11. So it's normally closed. You blow it up a little bit. And the location for it is going to be on page 4, C2. Again, we're on page 4. And if you go to C2 in this area, of course, it's a little bit C2 in 3/4 maybe, but that's okay. C2, it'll show you that that's the contact for the K18. So you have the solenoid over here and you have the contact over here. So it goes through this 250 amp disconnect. Then it goes through, it taps off 2 lines, goes through a 6 amp breaker, which goes to a transformer. The transformer is 460 on one side, 220 volts on the other side of it. And down here is your ground. So you have 0 volts for your ground. And again, the symbol showing you that it's going to ground. This is a 100-watt transformer. And that goes through this 6 amp disconnect, and it feeds both G1 and G2 power supplies. This is your 24-volt power supplies for your machine. Keep in mind, something that people aren't aware of is that if you follow this line and it's still 220 volts, it's going to go to, getting your power supply, which I already did, sorry about that, but that's not what I want to show you. It goes here to all your cabinet fans. So all your cabinet fans are 220 volts, not 24 volts. Again, be careful when you're opening the cabinets. If the fans are running, that you don't go and touch any of the terminals or the little connectors on the fans, because that is 220 volts. It is protected by a 2 amp fuse, but by the time the 2 amp fuse kicks out, I'm sure you'll feel the 220 volts. It's always advisable whenever you're doing any electrical on this machine or on any machine is that you disconnect the power from the source and lock it out, following the proper lockout tagout procedures. On this G2 power supply, it also charges the battery that's inside the cabinet. And from there again, your power is going to be going out to your 24 volts, C, C plus, B minus, and B plus. Again, keep in mind about this, the way they indicate the power for 24 volts. They don't put C minus and B plus, or, I'm sorry that doesn't, or B plus. They just put C. They'll put a C, C plus, B minus, B. So keep in mind that this C is a C minus, this B is a B plus. Why they do it like that, I don't know, just to confuse me, I guess. This is your phase sequence relay. So if you ever hook up the power and you do it backwards, that's the thing that's going to tell you, hey, the phases are not right. And you also have this going to page 5, which is the next page, and that's going to RST. It's going to be page 5, B1, B1, and B0. All right, so page 5, B1, B1, and B0. Again, you have your cross-reference. It's coming from page 4F9, page 4F8, page 4F8, and you have your RST and your ground. So each line from there feeds through this KM1. KM1 is your contactor when you push your drive energize button. It goes through Q2, which is 225 amp disconnect. Goes through your line filter and your reactor. Which also feeds the KEB drive. So on the electric machines, unlike the Mars machines, the drives, line 1, line 2, line 3, are only fed to the injection drive, which is a 132 kilowatt drive, which is quite a big drive. From there, what they do is, because the first drive is going to be the master drive, these are going to be the slaves. It feeds the power through this plus, plus, minus, minus. So that goes to the plus, plus, minus, minus here, goes to the plus, 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 minus, minus there, here, and any drive that's in the system. What is the plus, plus, minus, minus? The plus, plus, minus, minus is a DC bus. So going out to the drives, we're feeding DC power, and you have a big fuse box inside the cabinet that has the large fuses for the three other drives. Sorry. So this one is a 200 amp fuse, two 200 amp fuses in that cabinet, two 250 amp fuses in this one, and two 80 amp fuses. All right. This squiggly line down here, I'm going to explain in a minute. So what happens with an inverter? What an inverter really does is it takes an AC signal. An AC signal is 60 hertz. It goes like this, three phase, so it's going to be three of them. And you have a 0 volts here. You have a plus 480 volts here, and a minus 480 volts here. So what an inverter does, it actually takes this signal over here, the negatives, and inverts them. So what you have is all positive values for your signal. So it takes the signal from three phase, line 1, line 2, line 3, which is an AC 60 hertz signal, goes into this rectifier system. That converts it to a DC signal. So eventually, after it's done going through the whole converter, it'll actually be a solid DC signal. Now, what's the voltage of this DC signal? The voltage of the DC signal is going to be the incoming power, which is 480 volts, or whatever your incoming power to the drive is, times 1.414, and that'll give you your voltage for your DC bus. So that's the DC bus voltage. So if you ever want to check the DC bus, all you have to do is do the multiplication, take your incoming power, times it by 1.414, and you'll get what your DC bus voltage is. You should have 679 volts DC. So why 1.414? Because 1.414 is the square root of 3, and it's a three-phase system, so that's how you get the 1.414. All right. You also have your VRAM bus system, which communicates from your controller, your CPU up in the cabinet. Oh, CPU. Long day, sorry. And down here, you have a brake resistor. This brake resistor, what that does is, because there's large capacitors on these drives, if you didn't have a brake resistor, a place for them to dissipate, when you disconnect the power off the drives, they would still be live. And also, this also helps stop the motors and stuff like that. So it's used for various things, but the most important one is to dissipate the energy out of the drives. It also dissipates the energy and helps the motor stop exactly where they're supposed to stop, but that's a different thing. We won't discuss that. The other thing here is you have a T1 and T2. So T1 and T2 is a thermistor, which is located on the motor itself, and that keeps track of the temperature of the motor so we don't overheat the motors. And then your line 1, line 2, line 3 or TUV becomes UVW. And you also have an encoder. Your encoder here, it goes to the motor, which keeps track of the position of the motor at all times. All right, again, it's the same thing, except no line 1, line 2, line 3. All you have is the DC bus being fed to the drives. So what the drive does after it gets this DC signal, it then converts it to an AC frequency. So I believe the frequencies are up to 1,000 hertz. Sorry about that. I try to disable the phone from doing that, but it doesn't always work. All right. I lost my train of thought here. All right, so then that goes into this KE3231, which is on page 4. Again, that's your phase sequencing. All right, on here for line 1, line 2, line 3, you're also feeding this transformer T2, which is for your injection unit die height motor. And the way this die height motor works is it actually takes the signal to go one way, and so this will make it go forward, and this, by reversing the two lines, it'll make it go backwards. Well, that's for the injection. I'm sorry, that's the injection unit. This one's the die height. I can't read. Sorry. And again, you have your injection unit fan motors, your clamp motors, and your plastification motors. And those are all protected with a 1 amp fuse. And it's going through K19, 20, and 21 relays. This is your heater band circuit. The nice thing about the heater band circuit, what they do is they actually tell you what the size heater bands are. So, for example, E11 is a 36 by 45 millimeter heater band, 200 watts, and 230 volts AC. Down at the bottom, it tells you what the length of the thermocouple is. So B2 length of the thermocouple is at 2.5 meters, and these are K thermocouples, not J. The reason why they use K thermocouples is because they're more accurate than the J thermocouples, and they have a higher tolerance for heat. So you can actually have a lot more heat. You're not as restricted as you are with the J thermocouples. And again, this is the heater band circuit. I'm showing you the actual wiring diagram and the plug connectors. And these are your SSRs, solid state relays, which open and close to turn the heats on and off. And you have your fuses, your 30 amp fuses for the circuits. Another thing to keep in mind, they use the 3 phases of the system for this. So they have phase 1, phase 2 is for ground, I'm sorry, phase 2 and phase 3. That being kept in mind, one thing you have to be cautious of is this heater band, because it has a grounding system on it, if the heater band would ever go to ground, which is this one, I'm sorry, it would also complete the circuit, even if the power was off going to this heater band, because it's a complete circuit. The only reason it would stop it would be if this K1, if the grounding was caused before the power, not the return. If it was caused by the return, then what would happen is obviously you'd have a complete circuit. So for example, this is line 3, and this only has a fuse on it. And if it goes here, and if it goes through the grounding, because it's shorted out, it'll complete the circuit. So again, that's another thing that you have to be cautious of if you have a runaway heater Again, it could be either the solid state relay being stuck, or it could be a short circuit on your heater band. Assistant power sockets, below the injection unit, there's a cabinet. Inside the cabinet, there's a box. The box has these assistant power socket connectors. That's not, it's actually on a 30 amp and 216 amp breakers. The problem is these are not calculated in a full load amperage of the machine because technically they're not installed. They're just there in case the customers, if you guys want to use them, but they are there for, you can actually break into the circuit and install a 30 amp plug, 3-phase, or two 16 amp plugs. I do that when I go to a show. I'll actually use these circuits, and I'll run my plugs for my dryer, my thermolators, my mold heaters, whatever. I'll just tap right off of those circuits. Makes it a little easier. This is the optional hot runner circuit. Again, it has another transformer. It'll be a T3 transformer, which is a 33.5 kilowatt, depending on the size of your heater circuit, your hot runner circuit. And these guys are options also. These are optionals if you want 220 volts or whatever. Okay. Yesterday I was telling you about the STO problem. What the STO is this not right here. These inputs, if you look where they're coming from page 13, Q9. 13Q9 just so happens to be the safety relay circuit from the pills. Like I told you yesterday, the STO errors are caused by these safety circuits not being energized because there's a problem with the pills, which is causing the safety circuit relays not to close. So that'll give you your STO errors. So this power, and unlike the one for the Mars machines, the contactors or the relays, safety relays, they actually control the valves. On this machine, they control the inverter signals. So if the safety relay isn't satisfied, then the inverter will not get its power to 909, 900, 907, 906, and 908. And it'll produce an STO error, which means it's a safe torque off. So anytime you have a STO, that means the drive is disabled and cannot run at all. You actually have to put the signal on these X2B, X2A, on the X2B circuits. All right. Next on, you have the main control circuit. You got your heater. When you push the button for the heater, it closes KH1. This is your main start circuit. If all of these contactors are satisfied, then the start circuit will start. Mold adjust forward. Mold adjust back. Injection unit forward. Injection unit back. And you have this K13, which is on page 11, F4. So we're on page 11. F4 is this guy right here. That's just a safety that's coming off of 24 volts to make sure that the power is okay. It just checks the power for you. All right. This guy here is a safety relay circuit. Again, we covered this yesterday. This is the pills. And these are your 900, 901, 902s, which is your safety relays. So you have your main contactor feedback, injection unit contactor feedback, your front doors, your rear doors, your e-stops, your mechanical bar, which is your drop bar, purge guard, roll body stop 1 and 2, top guard, another drop bar, and then again you have all your outputs. All right, how does this guy work? This guy works off of this signal right here, this T0 and T1. You cannot just put 24 volts on any of these inputs up here. All of these are inputs. So this is input 2, 3, 4, 5, 6, 7, etc. They are going through the circuit through a pulse signal. This is T0 and T1. So it's not a straight 24 volts. So for example, T0 will go up here. It'll come down to this guy, come down to this one, come down to this one, and come down to here. The T1 on the dual channel circuits, it'll do every other one also. So what it's looking for example, the front door has T0 and has a T1. So inside the safety unit, there's 2 CPUs. They're different CPUs. So you have CPU 1 and CPU 2. And what it does is it takes each one of these signals and goes to each one of the CPUs here. Each goes to here. And if they're both equal and they match, then you'll have an output. If you don't have a signal that matches what the signal is supposed to be, then you won't get an output, and your safety relay will go into an alarm. You'll have an I fault, and you'd have to open the door, reset whatever caused the input fault. All right. Again, keep in mind when you're looking at these things, for example, the front door. Well, it's a normally open circuit. So why am I getting a signal in 801? Well, when you close the front door, this is going to close. And when you close the front door, this is going to stay closed. So it knows to check to make sure that it has the signal at all times. So when you open the door, this one's going to open, and this is going to open. So it kind of does the opposite of what you're actually thinking of. In order to get a signal to any one of these connectors, you obviously have to have all the switches closed. So in order to have all the switches closed, they have to change status. You have 2 e-stops, 2 front doors, and 2 rear doors. The reason for that is those are the 3 different areas where the risk factor for severe injury or death could occur. So what they do is they make sure that the safeties are working properly. So they have dual channel for the front door, dual channel for the rear door, and dual channel for the emergency stop circuit. Again, this is the safety relay that we just talked about, which controls your drives. So if you can't operate any of the drive functions, it's because the safety relays KE2 and KE3 are not energized. Again, they're not energized because there's a problem with the pill safety circuit. Again, with this new pill safety circuit, all you have to do is open a cabinet door, which is kind of tough because it's protected with that switch. But if you can do that without tripping the switch and looking at the pills, you can actually read what the problem is. Yeah, that's good. This is the loop pump circuit for the clamp. And again, this is just a controller view of the hookup for the controller. This is the digital input signals. Again, we're using PNP proc switches, and the proc switches control the mode adjust forward, mode adjust back, eject the unit forward, inject it, product drop check, nozzle touch check, injection forward end, suck back end, your mode adjust forward and back, and your ejector backward end. Again, down here, you'll have your front safety door closed, your rear safety door closed, your injection guard closed. On the Mars machines, those signals, the safety, front safety door and rear safety door signals, they don't go to the CPU. They only stay on the pills, and therefore it'll give you a safety feedback abnormal error. Digital input 2, you have your mode close enable, mode area free, robot home, ejector back enable, ejector forward enable, your 2 cores in and out enable, complete mode open enable, core in end, and your robot emergency stop, your motion, your cycle stop, cycle start. Digital input 3, just another more inputs. You have an injection unit rotated, top guard safety, lubrication pressure relay. So if you run your auto lube and there's a pressure sensor in there, if the pressure sensor up here does not close during that cycle, it'll give you a low lube alarm. So that'll tell you that the lubrication level is low, that it's not going through the circuit because the pressure sensor is not seeing the pressure of the lubrication pump. Lube level, phase sequence monitor. You have core 3 in and out. Front safety door, if you have an electric door. Rear safety door with the electric door. What those do is they keep the doors from opening after you put the machine in cycle. It locks the door with an electronic lock. Loop pump, safety relay feedback, core pump abnormal, water filter, which isn't on these machines, mold open end, injection screw fan warning. Digital input 1, you have your motor start and stop, mode adjust forward, mode adjust back. I think we already did this one, didn't we? No. Injection unit forward, injection unit back, injection unit braking, lube motor, air blower 1, 2, 3, and 4, valve for hopper, red lamp, shut off nozzle, open and close. Now, on the machines, there's only 2 air blows, 1 and 2. That being said, if you go to the digital output module G3, pins 11 and 12 should be free, and you can add 2 more air blows. Same with your shutoff nozzle. Yeah, you don't have a shutoff nozzle, but the output is still there. It's going to be on G4, pins 15 and 16. They give you the software for all of these functions, but they don't give you the hardware. It's an option. So if you want to add hardware, it's pretty easy to do. Again, the shutoff nozzle can be either hydraulic or pneumatic. It doesn't matter because it's just a signal, 24 volts, going to a valve, opening and closing the shutoff nozzle. Whether it's pneumatic or hydraulic is irrelevant as far as the signals go. Digital output. Again, you're doing outputs now. So your mold open end is going to go to K80. Eject the backwards, K81. Eject the forward, K82. Core out, K83. And again, these solenoids control these contactors right below it. And again, it's your page and your reference for your, so this is on page 23-1, field 5, F5. All right, you have your core ins and outs. Then you have your buzzer signals. Over here you have your heater circuits for your rear zone, your front zone, your nozzle zone, your center zone, your hopper, etc. These are all your thermocouple inputs. And over here you have your outputs going to your SSRs. There's a multi-IO, which is both analog and digital. And again, the difference between analog and digital, analog is 0 to 10 volts on this machine. Digital, it's on or off. So a digital signal is just two status, so either it's on or it's off. An analog is a range from 0 to whatever voltage you have. So that's how all the transducers work. They work off of voltage. For example, see, this load cell right here is for your injection pressure. And what it is, it's just like a scale. So if you step on a scale, you're going to get reading numbers 0 to, like my weight is 120 pounds. Don't laugh, everybody. But anyways, what it does is it takes an analog signal, 0 to 10 volts, goes into an amplifier card and it takes that signal and says, okay, if it's 1.62 volts, that equals 250 psi, theoretically. And that's how you get your pressure readings on these machines, because again, the Venus machine is all electric. There's no flow, there's no hydraulic flow except for a ZE machine, which has hydraulic flow, but the electric machines don't have hydraulic flow. It's all mechanical torque. So they use this load cell to take the theoretical mechanical torque value and creates a theoretical pressure value. To prove it, just go up to your injection unit, bring the carriage forward, and look at the pressure as you bring your carriage forward. Your injection pressure will change, especially when it hits the mold, because you're exerting force on this load cell, which creates the voltage differential, which creates a pressure reading. Again, you got a mold adjusting coder. That's new on the new machines, which is great because it does your auto die height really quick. And you have your injection motor cooling, your core pump switch. The core pump switch is an option on the VE machines that if you have the hydraulic power pack, that turns the power pack on and off. And here's your robot interface plug. This is a Euromap 12. It's a 32-pin connector. We're going to be switching to Euromap 67 soon. I think some machines are coming in Euromap 67. The difference between 12 and 67 is this is a 50-pin connector, and this one's a 32-pin connector. It also has, Euromap 67 has dual channel e-stops, dual channel front door, dual channel rear door. Whereas if you look, Euromap 12 does not have dual channel. It just has your e-stop signal channel, machine safety equipment single channel, and everything else is all single channel. Again, you got your robot e-stop single channel, and that's it. This is the core plug. for your core pull. This is your second core pull plug. This is a digital input if you have an optional digital input. This is another digital input 3. They added this for the injection unit rotate, the loop pressure relay, loop pump level. That's basically what they added this one for. And you have your digital output 1, digital output 2, temperature module, an analog module for your load cell, multi-IO. What this is showing you is all the different optional modules you can get. Your core pull plug, again, another option, robot plug. All right, any questions on the Venus machines? I'll take questions now, and then we'll cover the differences between the VE and the ZE on the drawings. It's not that many differences, but there are a few small ones. Questions? Oh, you have to ask the questions. I can't read the. Jeff has a question, right? So I notice your assistant power page, you mentioned hot runner power. Yeah, you can use your hot runner on there too. Let's see, can I use hot runner here to power auxiliary hot runner unit and have the machine turn those off in the event of end of run or other errors? There's a way, Jeff. I'll have to think about it, but yeah, I believe you can. You can actually hook up your hot runner system to the existing temperature systems if you have a spare, and that'll help you with the end of run, your end of run errors and stuff. But I'll give you a call after this meeting and we'll discuss it. All right, any other questions? Good. I'm doing a good job, I guess. All right, the ZE machine, again, the difference between a VE machine and a ZE machine is the ZE machine has an integrated core system, a hydraulic system, I should say. That runs the carriage, it runs the ejectors, and it runs the core. Again, you have the same symbols, same stuff here. Same sequencer, main power is the same. So the difference is, again, you have this inverter for the pump system. You have a gear pump instead of a servo motor. It's a hydraulic gear pump system. And all right, here's the one difference. Because it has hydraulics, you have a J5 card. Because of the hydraulics, what you have is a pressure sensor, which is an analog signal. The pressure sensor is 0 to 10 volts. 0 to 10 volts. And it needs this J5 inverter signal, which takes the analog signal coming off the machine and converts it to a signal for the KEB drive. So on the KEB drive itself, it's going to have a J5 card. Here it is. So what this does is it checks the injection pressure sensor, the ejector position, etc. But it also has inputs for It's not on here, but the inputs it'll have is for the injection pressure, the sensor for the ejectors, etc. They're calling it injection pressure sensor, but it's actually a sensor for the system itself. I believe they put injection pressure sensor because it's they're assuming it's a Mars machine. They didn't want to change the prints or something. But basically, that's the only difference, is it has an extra card in it, which I'm trying to look for that drawing, and it has a pressure sensor. So the system knows what the actual flow is out to whatever device it's operating, for example, the carriage or the ejectors or the cores or whatever. It'll actually keep track of the velocity of those systems. Yeah, I don't think I have, it's labeled wrong on this drawing, but that's what it's for.